today's after some lengthy 3 weeks break. I think we have a quorum, so we can start, then others can join us. I have issues with my camera, but I hope the sound is okay. I hope you can get me well. My camera seems to have an issue. I don't know what it is. Nonetheless, I think we can continue if the sound is okay. We'd arranged that we have double lesson today and a triple lesson tomorrow. We are still going to have it, but I think from next week we'll go to our normal routine. That is, we do the Wednesday single lesson, and then we do Thursday we can do the double lesson. I think we can do it in the morning, so that you don't have the evening one, because my understanding is the semester, I have not gotten the memo, but I understand the semester has been extended, so we will not try to recover the lost time. I hope I'm right. I don't know. I don't have the dates, so I don't know is extended up to when or by how many weeks. But I suspect it is by 5 weeks. Somebody can confirm that if that's the case.
We've not yet received official communication for the dates, but I'll let you know once official communication is out.
Okay, thank you very much. Yes, once the official communication is out, you can let me know if I don't get it. So today we decided we are going to look at difference equations and the introduction to digital filters. Actually, the topic should just be introduction to digital filters, because we are looking at difference equations. We are not going to solve difference equation, because that is something you can encounter in maths. But for us, we are more interested in difference equation is to describe an LTI system, and specifically a causal LTI system. And we are going to notice that in the difference equations, we don't have future samples. We talk about the past samples. So basically, we're dealing with the systems that are causal. So we are going to look at, we're going to have a very brief introduction to filters, how the difference equations come in, the importance of difference equations in digital filters. Then later we are going to do filter design. We will not go into very sophisticated filter design, for the simple reason that, as I've said before, this unit is not DSP. DSP, just part DSP. So we will not go to the details in designing filters like the DSP, like a typical DSP class. However, we are going to look at design of a simple low pass filter. We may also look at design of high pass filter, from the low pass filter. We are going to come to that. Yeah, there are methods which you can convert a low pass filter into a high pass filter. We are also going to look at designing a low pass filter or a system which is described, with the analog transfer function, which is basically the Fourier transform of the, not the Fourier transform, actually that should be the Laplace transform of the impulse response, because in the digital domain, we'll be working with the transfer function in the Z domain, in especially when it comes to realizations of the filter. We are still going to use DTFT in the design, but we are going to look at the Z domain when it comes to realization and also implementing the filters, creating the structures for the digital filters. We're also going to look at how you can convert, given the transfer function of the analog transfer function as the Laplace transform of the impulse response, how you can convert that into transfer function in the Z transform. Yeah, we're going to look at a method called bilinear transformation. Probably you have touched it somewhere, but we are going to look at that. At least that will give you enough knowledge to be able to do your labs. Although I checked, I think you are implementing, you are doing the labs in MATLAB, and I think from the filter design module in MATLAB, it doesn't require you to know much about digital filters. Actually, I try to have a look at it. If you have done filter design in the analog domain, probably you don't need.
Excuse me, sir.
Yes.
Could you please let Emmanuel in?
Oh, Emmanuel.
Yeah.
I'm not seeing anybody who is trying to come in. That is interesting. In my screen, there's nobody who is trying to come in. Tell him to try again because I can't see him.
Okay.
All right. Yeah, so that's it. We'll spend probably 2 weeks on filters, and I hope that will enable you to do your labs. As I said, actually, the digital filters are not in the syllabus. The only ones in the syllabus are the standard 2D convolution filter, which is very simple to implement. Yeah. Nonetheless, due to your labs, we'll get into this. Actually, we used to look at it, I think, the first few years, but later we have just been looking at this topic. But now we are going to do examples of design. We have not been looking. We have not. So, what's the difference equation? Is a formula for computing an output at time n. We are talking about digital, so we are talking about time n. the index, time index, based on past and present input samples and the past output samples in the time domain. Yeah. And this equation, different equation for LTI will be of this form. Y of n. So you have the present and past input samples, and then you have past output samples. You are expressing the current output as a summation of the present and past input samples and past input and output samples. That's what it means, and so it can be expressed just as a summation. That will be the summation of I to M, BI, X, and this is a delayed samples xn minus I minus, yeah, the summation of j is equal to 1 to n, aj of n minus j. So the BI are the feed forward coefficients and aj are the feedback coefficients. So, of course, this can also be written. You see, in this case, we have y of n is equal to this. That can also be written in this form, where j goes from 0. You can see in this case, j was going from 1 to n, but now you can also have j going from 0 to n, ai y of n minus j. This. So you can also put it in this form. That's simply adding the yn to this other and just adjusting your limits to go from 0 to n, where m is equal to that and aj is equal to that. I think that is we are going to see more of this. Oh, sorry. Give me this person. And actually, there's not much to say about this. I think we can just look at an example, a very simple example. We are going to look at more examples later. You can look at a very simple example of a difference equation where you're given y of n is 0.1 x of n. So this is a b1, yeah, and this is a 0.2. Well, this will be b0. This is 0.2 x of n minus 1, and this is 0.8 y of n minus 1. It has got a delayed sample of y with some feedback. So specifies the digital fearing operation where the coefficients 0, 1, 0.1, 0.2, this 0.2, and 0.8 fully characterize the filter. The yn minus 1 samples is feedback. If n is equal to 0, it means that we don't have feedback. Yeah. If n is equal to 0, if n is equal to 0, of course, it means we have no feedback, and of course we call the filter non-recursive filter or a finite impulse response. Yeah, and this we are going to mainly look at design of FIR filters. We may not get much into IIR, but we will mainly look at the FIR. So BI coefficient, yes.
For the coefficient B1, I mean A1, will it
Yeah.
be 0.8 or negative 0.8?
A1. This should be negative 0.8.
Okay.
But we are just look at the absolute value. So n, if n of course is not 0, is greater than 0, the filter coefficient, the filter is referred to as recursive, also known as infinite impulse response filter. They are more complex, they are more unstable, but as we go on, we'll see why sometimes they are necessary, because we are going to see an example where they reduce the number of computations, because using the number of computations is very important when it comes to filters, because remember this digital filters work on samples of an analog signal. Yeah. So, and from what you can see here, you can see that Y of n is a summation of the current X input sample, past output samples, and also past input samples. So all that computation has to happen within one sample period. Yeah. So all that would have to happen within one sample period. You have to do all that computation, all that summation has to be done within a sample period. So so sometimes it's necessary to be able to, where you can, use IIR to cut down on the number of computations, as we are going to see. So you can be given a difference equation, and from that you are expected, you can be able to move from difference equation to the transfer function in the Z domain. From that, you can be able to get the response of the filter, the frequency response of the filter, and we are going to see with an example. And so let's see. Here's an example. Well, this is just showing you exactly how you get the Z transform. You get the Z transfer function, the Z domain transfer function. You start by Y of n is equal to this. So you take the Z transform of your difference equation. Yeah. So Z of yn due to Z transform is linear. So Z of yn is simply the Z of the Z transform of each of these terms and then add them. So Z of yn is equal to Z of all these samples. So Z of yn is, now we have put is a Z transform of all the the samples, and of course that becomes, we know z of yn is actually yz. Yeah, so one is yz. Z of xn, x of n is, you can put the b naught outside, is b naught of x of z, and z of b1 x to the n minus 1 is simply b1 z to the power of 1 x of z, and you go up to b of m z to the minus m x of z, and then you subtract the y samples. Well, the delete samples of y. So that becomes a1 z minus 1 y of z. I think this is clear. And from this, you can bring the y of z terms to the left-hand side and combine them with yz. So you're going to have y of z into 1 plus a1 of a1 z to the minus 1 up to an z to the minus n is equal to x of z into b1 plus, oh, this should be b naught. This should be b naught. I'm not seeing this. This should be b naught because of b naught of x of z plus b1 z to the minus 1 up to bm z to the minus to the power of minus m. So h of z is simply y of z divided by x of z, which is simply this. So you can be able to get your hz from your difference equation and vice versa. And of course, once you have your h of z, you can be able to find the frequency response. And that will be our next example. I hope so far everything is clear. I think it is clear. Since we have already done Z transforms, I think this should not be a problem. Yeah. So if there are no problems, we can continue. So here is a simple example. In this example, you are given a log TI system represented by a difference equation. Sometimes the equation may not be directly in the form of y of n is equal to something. Like here, you can see we have y of n terms on one side and x of n terms on the other side. So y of n minus 0.5 y of n minus 1 is equal to x of n. So find the frequency response h of omega, the amplitude response as the absolute value of h of omega, and the phase response. So that's what we have been asked to find out, to calculate in this case. So the Z transform, you just do the Z transform of both sides. So this becomes y of z minus 0.5 z to the power of 1. Y of z is equal to x of z. I think nobody has a problem with this. Yeah. Y of z, you can put y of z outside. So y of z into 1 minus 0.5 z to the minus 1 is equal to x of z. Therefore, y of h of z, which is y of z divided by x of z, should be equal to, I think that's where we are, should be equal to this. Yeah. So once you do the z transform, h of z becomes this divided by this, which is this 1 over 1 minus 0.5 z to the minus 1. To find the frequency response, you need to replace z with e to the j omega. Yeah. So h of omega, or e to the j omega, is 1 over 1 minus 0.5 e to the j omega. So that is a frequency response. Yeah. So we have got that one. Then the next one is amplitude response. Amplitude response, if you have a complex, you have a, yes?
For the previous answer, it had to be e to the power of negative j omega, since z is to power minus 1.
Yes, you are very right. This to be to the minus j omega. Huh? Z is e to the, no, z is e to the j omega. If you replace, because in the z, no, you can replace this with z e to the j omega. I'm trying to think whether we should replace with it to the j minus j omega, what that would mean. But I think if you compare the two, equations, that is h, if you look at h to the, whatever it is, let's just use h to the j omega. That should be, what? The integral of x. Oh, it's not the integral, it's summation, sorry. I'm trying to compare the two equations. H of z, that should be this, isn't it? X of n z to the minus n, z to the power minus n. And the other one is minus j omega. So actually z is e to the j omega. Yeah. So I think this is okay. So you can replace z in this case with e to the j omega.
And what of, since z is to the power of negative 1 in the formula for hz?
Z is equal to?
In the formula for hz, it is 1 over 1 minus 0.5 z to the power of negative 1.
Oh, z to the power of negative 1. Ah, I see what you mean. Oh, that's what you're saying. Oh, so this is to the j omega. I get you. I thought you were saying, talking about here. Okay, yeah. Here, this should be the minus. Yeah. I don't know what that means for our calculations. We must have missed somewhere. So thank you very much for pointing out that. Yeah, I was thinking the issue was whether should be e to the minus j omega or it should be e to the j omega. So h of omega is equal to this, which of course we can write this e to the j omega. We can use the Euler, so this becomes cos cos omega minus j sine omega. Yeah. Oh, this should be yes, which of course this becomes from here. Let's see from here. It becomes this. So the magnitude should be the square root. If you have a complex, if you have this complex number, what of course this becomes the magnitude of this simply the square root of x squared plus y squared. So we must put this in the form of a plus jb, yeah, or x plus jy, yeah. So we must put this in this form. So we have to rearrange this. So this becomes 1 minus 0.5 cos omega minus, this should be 0.5 minus j 0.5 sine omega. And if you notice something from your side, just tell me, because once you have made something, once you have done the notes yourself, it always looks right. So you may see something which I'm not seeing from my side, so you can raise it up. So the magnitude is simply 1 over square root of that. Yeah. So that is the amplitude response. I hope that is from your side you are getting the same thing. The phase response, h of omega, is 1 minus e. Oh, did you correct what that problem where we had minus? Okay. Oh, it was okay, because I think that's why we end up getting this. Yeah. Okay, that's why we end up getting this here. So I think from here there should be no problem. Once we correct there, then that's how we end up with this. Yes. Yes.
I think the last, the second answer for h omega should be plus j sine omega.
This should be j sine omega.
Yes, plus 0.5 j sine omega.
Oh, this should be plus because there was a minus here. Ah, thank you very much for putting. There was a minus here and a minus here, so this should be plus. Okay. But I guess from here we are okay. So h of omega is that. Yeah, that should be okay. Thank you for pointing out that. Phase response, h of omega is simply, when you have it in this form, denominator and numerator, the angle is simply the angle of the numerator minus the angle of denominator. If you're looking for an angle of a fraction, so normally it will simply be an angle of numerator divided by an angle of denominator. So the angle of x plus dy is tan, inverse tan over x, and the angle of h. So the angle of h omega, of course, this is a real number, so the angle is 0. So it will simply be 0 minus the angle of x plus dy, which is this. So that is our answer. Those are our three answers. So these are the kind of problems you may get. Where you're given a difference equation and you're expected to work out the frequency response, the amplitude response, and the phase response. Later we can look at other examples. So I hope so far so good. Now we are going to look at a block diagram of a linear, and actually what we are dealing with here is linear constant coefficient difference equation. I have not been mentioning this. LCCDE is linear constant coefficient. Because the system is, we are dealing with the linear system, the coefficients don't change. They don't change because they are part of the system. So it's constant coefficient, coefficient. So we have seen this already. That is this summation of this is equal to summation of j is equal to 0 to n aj of n minus j is equal to summation of I is equal to 0 to m bi x n of x of n minus I. We have already dealt with that. So the filtering operation normally has 3 stages. Again, we are going to look at that in details. It has 3 stages. There's the summing, because you are doing these summations. There is scaling these coefficients, and there is delay. This delay, yeah. So that will be actually the complete filtering operation, yeah. So, like in this case, what you have done, we are having a block diagram of a system represented by this difference equation. I've just written it in a different form, 3x sub n minus x sub n minus 1. Sometimes you can have this kind of representation, or simply x of n. Yeah, that should not cause any confusion. And this is x of n minus 1. So it may be represented in this form, x of, or it will be this x sub n, x sub n minus 1. So y of n is 3x sub n minus x sub n minus 1. So we have the input x, then we are scaling it by 3, multiplying it by 3, and then we are summing with a delayed version of x. So what you have here is a delay element. So whenever you have x n minus 1, it means you have one delay element. And what we are going to find out is, when it comes to realization of when you are drawing the structures, if you have x n minus 2, it means you have 2 delay elements in series. You don't put z to the minus 2. Normally, you normally put z to the minus 1, a delay, and another one in series. Yeah. So you have z to the minus 1, which is actually this. And then what we are summing is the negative of x sub n minus 1. So you have to do, again, scaling. To make it negative, you scale by minus 1. And then you get the sum, so that is the output Y. So the block diagram of this system represented by this is this one. So again, this can be a problem you can be given. Of course, more complex problems, we are going to look at it when we are doing different type of structures for digital filters. But generally, that is those are what the blocks you will find in a block diagram of a filtering system, of a filter. Yeah. So I hope so far so good. I also hope you are revising when you didn't have classes, so that you have not lost the momentum. So let's look at, if there are no questions, we can look at the digital filters. I can say a few things about digital filters. Of course, the purpose of any filter is to remove or keep certain parts of a signal. That is the purpose of a filter. And of course, filters are very important when it comes to our communication systems. It may be you want to remove noise. It may be you want to remove harmonics, because sometimes when a signal passes through a system, you end up having some harmonics, and you want to remove them so that you remain with only the fundamental, I mean, the signal you're interested in. It can be a bandpass filter, like a signal has passed through a system, and therefore it has noise. And you know, noise has got a constant power spectral density. So you may want to remove what is outside, because noise has a constant power spectral density, and you don't want to carry that power. You don't want to process that power or carrying it to the next section. So you'd have, for example, you use a BPF filter, but you filter whatever is outside the band of interest. So filters will have a lot of applications in communication system, and that's why they are very important to us, and more so digital filters, because most of the systems we have nowadays are digital, and I think we have looked at the reasons why they are digital. There are many other advantages of digital. So we'll be used to use digital filters. Yeah, and that's why there is all these methods to convert from to design digital filter given certain parameters. So there are broadly two types of filters, analog or digital, and our main interest, of course, is the digital filters. Analog filters, of course, which I'm assuming you have already covered somewhere along the way. They use electronic circuits. They are those passive filters which use capacitors, inductors, and resistors. And I think you have also covered active filters that use active circuits, transistors, diodes, and all. So a digital filter uses a digital processor. So that can be either a computer or it can be a specialized digital processor. Yeah. And of course, you can be sure there will be a lot of competition because when we do the filters, we are normally dealing with samples. And yet, those samples have been transmitted as zeros and ones. So it means when you are filtering, you have to go from your zeros and ones. You have to collect your zeros and ones and reproduce the sample and then do the filtering. So because computers don't understand samples, they understand zeros and ones. So there's a lot of processing when you do the filtering by a computer. Yeah. So this unfiltered signal, this is the filter. I think this is straightforward. So digital filtering, it could be a general purpose computer, such as a PC, or it may be simply a specialized DSP or digital signal processor. So in the digital filters, the signal is represented by a sequence of numbers. And those numbers will simply be referring to the value of the sample. Yeah. So the particular amplitude of that sample at that particular time. But still remember that the transmission is in digital, but when you come to digital filtering, you'll be looking at that, the value of that sample. So so that is a digital filter. You have an unfiltered analog signal. You go through an analog to digital converter. I hope you have looked at different analog to digital converter. Somewhere along your course, I'm sure you have looked at different ADCs. Yeah. So then you go to the processor, and then this is where you do the digital filtering, and of course, you get back to your digital analog. You go back to your filtered, to your analog signal through DAC. Because in most cases, the signal you're dealing with is analog, because this could be filtering an audio recording. Yeah. It could be filtering a video, a signal which has collected noise, which has been interfered with at the receiver and transfer and converted back to the analog. So that is the signal at this point. So the signal at the input will be something of this form, and the sampled signal is of this form. This is a filtered signal. Some things will have been changed here depending on your specifications, depending on your coefficients. This may have changed. For example, you can see this one was not, this originally was, maybe this originally was a sinusoid, which added, due to additive noise, you got this, but you're trying to filter out the noise, so you end up getting your original, sinusoid. Yeah, as we said, there is a lot of calculations. It involves multiplying the input values by filter constants That's what we were doing here. Remember, we are talking as this is a general form of a filtering system when you are given a difference equation. It's good to know that a difference equation is what is to digital systems. The differential equation is analog systems. So remember, you don't confuse the two difference equation and differential equations. So this is difference equation. So we are multiplying the input with some constant. Of course, the number of constants, the number of constants you are scaling with, or numbers you are scaling with, will depend on how many constants you have. How many, what do you call it? How many coefficients you have, yeah? Because like here, you have only two coefficients, yeah? This and that. So depending on how many coefficients you have, it will be quite complex.
Excuse
Yeah.
sir.
Yes.
What is the significance or the implication of a negative in the scaling coefficient or scaling factor?
In the scaling factor, of course, you see, the scaling can be, the coefficient can be negative or positive. I'm trying to think. The negative would mean it's going to affect certain frequencies negatively. It will kind of suppress them, and it will enhance certain frequencies. Positive when is a positive. Does it make sense?
It's okay, thank you.
Yeah, that's what it would mean. Depending on the coefficient, the filter behaves differently. The filter will have different cutoff. Yeah, yeah. We are going to see that when it comes to designing the filter. You're going to see in some cases you're going to have certain coefficients as 0, some certain coefficients are 1. And of course, when we put in the form of a difference equation, we only put the coefficients which are either positive or negative. We don't include the ones which are 0. Yeah. But remember, when you come up with the coefficients, you'll be having a number of coefficients. Some of them will be 0, so they will not appear in the difference equation. It simply means those others are 0, the ones which are not mentioned. Yeah. I think that will become clear when we come to actually designing a filter. So what are the advantages of a digital filter? One is they do not suffer from temperature variations. And that makes sense because if you are dealing with passive components like transistors, if they hit, the value changes, the value of the resistor changes, and of course that changes the filtering operation. Yeah, the cutoff may change just because the components have heated. So we don't suffer from digital filters don't suffer from, they are stable because they don't suffer from temperature variations. Digital filters characteristics can be changed with software. I think this is one of the most important factors. They are programmable and therefore are used in adaptive filtering. But an analog filter, to change the cutoff, you either need to change the resistor or you have a variable resistor, or a variable inductor, or variable capacitor. Indeed, like what we do in a radio tuner, the old radio tuners used to have variable capacitors. So you have some big capacitors. When you are tuning, actually what you're changing is the value of the capacitors. Yeah. With this is done by software. Yeah. Digital features are easily designed, tested, and implemented on a general purpose computer. Yeah, you can actually design your filter purely on MATLAB, implement it, generate your code for MATLAB, and you can implement your filter. Yeah. And even the filtering operation itself is done in the computer. But you can design and you can test. That's what you'll be doing in MATLAB. And then you can actually implement. You can use that code which you have generated to actually carry out filtering operations. Easy to sharpen the roll-off by increasing the number of delay elements. When you increase the number of delay elements, or rather when you increase the order for the filter, because the number of delay elements determine, well, when you have a higher number of delay elements, then the highest number determines the order. We are going to see. Yeah. So like what we have here, which is the example, this is first order, because the highest delay, the longest delay means n-1. This is the first order filter. Yeah. So you can increase the number of delay elements, that is, increase the order of the filter, and that will sharpen the roll-off. Once you understand the roll-off, what we are talking about is, for example, if you are having a low-pass filter, yeah, ideally, there should be a box car. That means at this cutoff frequency, you should get the stop band. We call this the pass band, and this the stop band. The stop band should be 0. You're getting completely nothing. Yeah. That should be the ideal filter, the boxcar filter. That if it doesn't happen, so we are going to see sometimes there may be ripple, and then there may be the transition, the roll-off. Now this roll-off, how sharp this roll-off is, depends on the number of delay elements or the order. Yeah. You want sharper, you increase the number of delay elements. Ideally, if you want this, you need infinite number of delay elements. Yeah. If you want, which is not realizable. So normally, how much delay elements is a compromise. Is a zone you make, but you don't want to increase because once you increase the number of delay elements, so many factors come in. Yeah, you need faster processors to be able to process that within a very short time. Yeah, as we said, within the sampling time. Yeah, so it's usually a compromise, the order. We are going to see that, but the higher the order, the better the roll-off, or the sharper the roll-off. What are the limitations? Well, I think by the time I did these notes, I think I did it from a textbook. So by the time that textbook was written, they were expensive. But now you might actually find that the components are so cheap that it is cheaper to implement a digital filter as opposed to analog filter. You might find that the capacitors and the inductors are actually much more expensive than the ICs, than these ICs, ADCs, yeah, yeah, ADCs mainly and DACs, yeah. The signal bandwidth of the input signal is limited by the capability of the ADC. Yeah, because the ADC will limit at what frequency you can sample. And what you're going to find, we are going to see physical, I mean, when you do calculations, is for a digital filter, the actual cutoff frequency depends on the sampling frequency. Yeah. Because you're going to find that, in fact, when you design, most of the design questions you get on filters may not even give you the actual frequency. They will give you the normalized frequency. Yeah. It's normalized against the sampling frequency. Yeah. So you might get something like you're given a pi by 4. Yeah. You're given you have to design a filter whose cutoff is pi by 4. That's a normalized frequency. Yeah. Instead of being asked, and that will be of course pi by 4 cycles per sample. Yeah. We are going to deal with that. But what I was trying to tell you that, of course, the filter will be limited by the capability of the ADC. How fast you can sample will limit also what frequencies you can be able to filter. Yeah. All computations must be complete within the sample period. Yeah. Remember that to be complete within the sample period. And it can be short. For example, if you are sampling at 44 megahertz or kilohertz, let's think of, what am I choosing? Kilohertz. Assuming you are dealing with audio signal, which goes from up to 22 kilohertz, so you'll be sampling at 44 kilohertz. So you'll be talking about such a very small period, 1/44 kilohertz. And all computation must be complete within that period. So it means these operations you are seeing here have to be complete within a sample period. All this to get that particular output of yn, all this must be done. And this is a simple filter. It must be done within a sample period. That's quite a major disadvantage when it comes to digital filters. Affected by quantization noise. Yeah. I'm trying to think whether this one refers to the quantization noise during the sampling. I mean, after sampling, of course, that would also come in. If you sample and you quantize, that would come in. But sometimes when we refer to quantization, we're also talking about the the length of the word when you convert to binary. Because of storage, sometimes you limit the length of the word. So you cut off some part of, maybe I can give you a good example. If you are carrying samples and maybe they have something, give a good example. Maybe in a computer, again, we are dealing with, even when you are storing, we are still doing zeros and ones. Maybe that's how you have represented your signal, yeah. And you decide you want to reduce the number of storage elements. So probably you cut it to this so that you don't have some, yeah, you don't have some, you are cutting off this. So of course the value, cutting off this changes the value kidogo. So that's what we talk about. Sometimes that is also referred as quantization noise. You know, the fact that you have cut off a part of the word, yeah, of what you have stored in the computer, yeah. So this could be referring to both the quantization after sampling, or quantization of this cutting off of some of the numbers. I hope you have done computer storage, different types of computer storage, how you keep the floating point numbers and all that. So I think from that you can see what I'm talking about. So the accuracy of the digital filter depends on the word length used to encode into binary. I think it's related to that. Initial design and development time for digital hardware is more than analog. Yeah, there's a lot of calculations to be done. So the initial design is quite some work compared to analog filters. So I hope so far so good. Any questions? It looks there are no questions. So how do filters work? Let the digital values transferred from ADC to the processor. You have these samples. I think digital output from the processor consists of these samples. The value of y is calculated from these samples. Filtering, yeah, I think basics, I've already talked about it. The filtering action depends on how you generate your y values. Y is the output. So how you generate the output value from the x values, yeah, and previous y values, like in the case of IIR. In FIR, you only have the x values. So you can have simple, we are going to look at different simple delays, simple digital filters. You can have a pure delay filter represented by this difference equation. Yeah, the first difference equation, y of n is x, n minus 1. Yeah. The output, so this is normally called a difference filter. The output at this time is simply the input at t is equal to this. This is what it means. It means the output is simply the input at t is equal to n minus 1 h. Yeah. Where the signal is delayed by time h. Yeah. So this is what we are saying. When you write this, that's what it means. The output at this particular time depends on what happened the last sampling period. That is y0 is equal to x of minus 1. In this filter, y of 0 is simply x of minus 1. Y of 1 is x of 0. Y of 2 is x of 1. Y of 3 is equal to x of 2. Yeah. So that's how the y output samples will be. Because y of n is x of n minus 1. Then you have the two-term difference filter. And this is a difference filter. It has two terms. It has the current x of n. This is minus, it's a difference filter, so it will be minus x of n minus 1. This will be, this is just a two-term, it's not average. This will be a two-term difference filter. So the output at t is equal to nh is equal to the difference between the current input and the previous input. So, and this circuit, actually this is similar to the analog differentiator circuit. Yeah. Then we have the two-term average filter. So for the two-term average filter, the output is the average of the current and the previous input. So you have x of n plus, there's no difference, this is average, plus x of n minus 1 divided by 2. I think this one is normally a smoothing filter. This is a type of a low-pass filter. It smooths out the high frequency variations in a signal. Order, I think we have already talked about the order of the filter. By definition, the order of the filter is the number of previous inputs used to calculate the current output. So in this scenario, there is a first order filter because there is only a single delay. Yeah, and first order filter. So, actually, you have given here, you are saying the ones given above, they are all first order filters. Yeah. So these are examples of first order filter. This is a first order filter. This is a second order filter. So if you are using a sample which is delayed, not the last sample, the last sample, then it becomes a second order filter. So this is a first order filter, a second order filter. This one is a third order filter. Yeah. So it's simply the highest, I don't know if it's the best term to use, the oldest sample. I think you can put it that way, which is used to generate the output. So digital filter coefficients, these are digital filter coefficients. Yeah. So like in this case, the coefficients were 3 and 1. So these are the coefficients. Oh, these are the coefficients. I think we are going to cover that. And of course, these coefficients fully define, characterize that filter. So how that filter treats or produces output or treats the signal which is coming into it depends purely on these coefficients. Then we have, I think the ones we have been looking at are their own and recursive. Yeah, so long as you don't have previous samples of YN, that is an unrecursive filter, and we call that filter FIR. These are things we know, recursive filter. And of course, when you have a recursive filter, the order is still the highest, whether it is from X or from Y. In a recursive filter, still the order will be the highest term. So in this case, they are both X of n minus 2. This is the delayed, 2 delays, and this is 2 delays. So this is a second order filter. So it doesn't matter whether the highest is coming from the X or comes from the Y. The order is from the highest or the longest delay. Yeah. What I've done here is I'm trying to give actually the advantage of a recursive filter by having this example here, where the output is simply determining by adding the previous 8 inputs. For an unrecursive filter, or rather for an FIR filter, to get y of 9, I mean, if you get this 8 sample, this 9th sample, you need to add all the previous sample, X samples from X0. But you could achieve the same effect with a recursive, which will simply be y of 9 is simply X of 9 plus y of 8. Yeah? Because up to here, this is y of 8. Yeah? That's y of 9. So up to here is y of 8, up to here is y of 7, up to here is y of 6. So to get y of 9, you simply get X of 9 and add to y of 8. This is a recursive filter, but you can see the amount. So the moment you get y of 8, you don't have to calculate, keep on adding this. Just get the value out of the value you simply received earlier and get y of 9. Yeah. So you can see that this is the major advantage of a recursive filter. It cuts off all this addition to simply this addition. Because what it would have meant if you used an recursive filter, as the sample increases, so y of 10, it means now all this plus y of 10. Y of 11 is y of 10 plus all this. So there's a lot of addition. It becomes very easy to achieve this. So do you have any questions? this is basically just introduction. So tomorrow we will look at how to design a simple low pass filter. Today I just looked at cases of maybe you're given one form of filter characterization and you're expected to work certain parameters. So tomorrow we will look at where you're actually given either normalized frequency or the actual frequency, and you are expected to generate the filter coefficients. I think you have already been informed by your classmate that the cut will be next week. We did it on Wednesday. It will be physical. It will be 12 to 1. But we also agreed that it will cover only what we have done up to the start of the strike. So this will not come in. I was requested that it doesn't come in the cut, and they acceded to the request. So for now, if there are no questions, just have a good day, and we meet tomorrow at 8 for 3 hours. Have a good day.